Welcome back to Online Calculus 2. In this online lecture, we're going to learn about our introduction to what infinite series are. All right, we left off in the last video, or our last class, introducing what we were calling a sequence, which was basically just a list of numbers. How we're going to transition from a sequence into what we're going to define as an infinite series is instead of just listing these numbers, we're going to add them up. So if we have terms in our sequence, A1, A2, A3, A4, and so on, we add them all up, A1 plus A2 plus A3 plus A4 forever, and that will give us what we're going to call an infinite series. All right, let's take a look at an example. We saw some sequences in the last video. Let's say we have the sequence here where the general term is 1 over n. So we start with values of n equal to 1, then go to 2, then 3, then n equals 4. We get these terms for the sequence 1, a half, 1/3, 1/4, and so on. Now, if we just take those terms instead of listing them and add them up, this gives us now an infinite series, 1 plus a half, plus a third, plus a fourth, and so on. That infinite series in particular, we're going to see come back in a following online lecture. All right, let's take a look at an example we saw earlier in the kind of introduction to sequences in infinite series, the one that came from what we were calling Zeno's paradox. So if we start with basically trying to walk a distance of 2 units, but split that into walking to the halfway point, we get these terms, 1, then a half, then a quarter, 1/8, 1/16, so on and so on. All right, and one way that we're going to look at infinite series, instead of writing out all infinite amount of terms, or even a few of them, is we're going to try to find a pattern or formula for the nth term, or the general term. There's 2 ways we can do this for this example coming from Zeno's paradox. If you take a look at your terms there, 1, a half, a quarter, and so on, like with sequences, we might want to start the starting index n with the value 1. All right, notice for this pattern, how we go from one term to the next is by taking half of that. So the general term here, we could think of it as being a power of a half. You see that there, a sub n, written as 1/2 to the n minus 1. But why we're not writing it as the nth power is, notice the first term is 1. So you might think, how can you get 1 as an exponent? Well, you can think of it as something raised to the 0 power. Notice there with n minus 1, at the starting index n equals 1, you get 1/2 to the 0, which is 1. This is one way that we can find a formula for the terms coming from Zeno's paradox. There's an alternate way to do this, which in my opinion looks a little bit nicer. We can write all the terms as a power of a half, but we start the index value with 0 instead of 1. Notice now that general form or term a sub n, 1/2 to the nth power, start with n equals 0, you get 1/2 to the 0, which gives you the first term in your infinite series, 1. So there's kind of 2 consistent ways we can do this, depending on how we want to start our starting index value. 1 is usually standard, 0 also occurs a lot as well for the starting index. All right, and what we're doing here is introducing, with Zeno's paradox, something called summation notation. So there's a few kind of different expressions appearing in here. That symbol there is the Greek letter sigma, which denotes sums in mathematics. All right, there's a few different parts there. The a sub n, that's referred to the general or nth term for that sum. We have in the bottom part, n equals 1. we refer to n as the index, and then the 1 there, that's the starting value for the index. Since we're dealing with infinite series, the upper quantity in the summation symbol, sigma, is always going to be infinity, since we're adding up terms from n equals 1, n equals 2, forever, going up to the final index value, infinity, which we'll never reach. All right, so how we implement this is we think of the index value as changing by 1 unit at a time. So here, if we start with the index value as 1, plug n in as 1 to that general formula for a sub n. Right now, we just get a sub 1. Now we move on to the next term where we plug in n as 2. We get a sub 2, and so on and so on. All right, let's take a look at some examples of basically just given an infinite series written in summation notation, writing out the first few terms. All right, so I'll maybe pause the video here, write out some of these terms for this infinite series. All right, this was the one from Zeno's paradox. Notice in the summation symbol for sigma, the index value starts at 1. So if you start with n equals 1 and plug it in, you should get 1/2 to the 0 power, which is 1. And then when n is 2, your exponent is 1. So you would have 1/2 to the first power. For n equals 2, that value comes out to 1/2. When n is now 3, you get now an exponent of 3 minus 1, 2, giving you 1/2 squared, which is a quarter. All right, we mentioned earlier, there's 2 ways that we could write the general term here for a sub n for the infinite series coming from Zeno's paradox. We could either choose to start the index with the value 1, or we could choose to start the index value with 0. Notice the general forms for the terms look slightly different. An n minus 1 power when the index starts with 1, or in my opinion, the cleaner and simpler version, the nth power, but now n starts with the index value 0. Let's take a look at a second example. So pause the video, write out the first few terms. All right, notice here we're starting the index value with 1. Plug in n as 1, you get 1 over 1 squared, which is 1. And then move on to n equals 2. Your general term gives 1 over 2 squared, a quarter, and then so on and so on. So you should get as your terms for this infinite series 1, then plus a quarter, then plus 1/9. 1/9 is 1 over 3 squared, and then so on and so on. This is one of my personal favorite infinite series. You may recall in our intro to infinite series and sequences, we said this series had a sum of pi squared over 6. This infinite series in particular will come back in other places in your journey, let's say through the calc sequence. All right, let's take a look at a third example. This one has a slightly different nth or general term formula. Notice in the numerator, we have -1 to the nth power. Now, as the values of n change, -1 to different values for the exponent, that's going to give you either +1 or -1, depending on if the exponent n is an even value, -1 to an even power will be 1, or if the exponent is odd, -1 to an odd power, like -1 cubed, will come out to -1. So pause the video here and write out the first few terms for this third infinite series. All right, notice for this one, we're starting with n equals 0, which does happen occasionally. So just make sure for questions you pay attention to the starting index, usually 1 or 0. All right, so if we start with n equals 0, you should get as your first term 1. The second term with n equals 1 should come out to negative 1/3, then positive 1/5. Notice the signs are alternating for the terms back and forth between positives and negatives. This is what we're going to call an alternating series, where the signs of the terms alternate back and forth between positives and negatives. All right, now that we have some examples of infinite series written in summation notation, that's just kind of the standard way we'll write them. We can get to our central question conceptually that we need to answer is, how do we add up an infinite amount of numbers? We can't sit there forever and just add one term to the next, because there would be no end at which we would hit equals on our calculator, for instance. So we need to introduce kind of an alternate way to deal with this. We're going to see sequences come into this, along with a concept of a limit. All right, so the basic idea to answer this, why we started in the previous online lecture with sequences, is infinite series, we're going to turn them into a sequence. And the name of what we're going to create is what's called the sequence of partial sums. All right, so let's go through this, introducing from an infinite series what the partial sums are. This gets conceptually a little challenging, so definitely go back and review this part of the video several times if needed. It's probably one of the more conceptually challenging parts of the calculus sequence. All right, let's start with a general infinite series here. How we define the partial sums, we're going to write these as S and then a subscript n, is what we do is just by adding up the first few terms. So we're going to talk about first the first partial sum, which is just adding up the first number in that infinite series. That first number is just A1, so the first partial sum, S1, is just the first term, A1. We now look at the second partial sum, which is adding up the first two terms of the infinite series, A1 plus A2. And that, again, we can understand that is a finite sum. Notice we're adding up now two numbers. We conceptually know how to add two numbers. All right, we move on now to the third partial sum, which is adding up the first three terms in that infinite series, A1 plus A2 plus A3. And at this point, you can probably see the pattern. What we're going to define as the nth partial sum is adding up the first n terms of the infinite series, A1, A2, A3, all the way up to A sub n. Notice here, even if n is a very large value, for instance, if we're talking about the 1/1,000,000th partial sum, 1,000,000 is still a finite number. So even if you were to add up 1,000,000 different numbers, that we can still do, since you're still adding up a finite amount of terms. Now what we do with this set of partial sums is we turn that into a sequence, what we're going to call the sequence of partial sums. And this, conceptually, we understand what we learned in our last online lecture is how to understand and work with sequences. All right, this is going to be where it gets a little tricky. There's a lot of referential definitions. So we'll be talking about infinite series, but we'll be referencing properties of them related to sequences of partial sums. All right, so the first part is we're going to say that the sequence of partial sums, if that has a limit that exists, so in other words, if S sub n, that form for the sequence of partial sums, if that has a limit, if it's convergent, then we say the infinite series is convergent. And what that sequence of partial sums converges to, that is mathematically what we define as the sum of the infinite series. All right, if that sequence of partial sums does not have a limit, in other words, that limit does not exist, the sequence of partial sums is divergent, then we say that the infinite series is divergent. And conceptually what this means in this case, if the limit for the sequence of partial sums doesn't exist, as you add up the terms in the infinite series, there's no sum. So in this case, if the infinite series is divergent, there's no, I'll say conceptually simple way to understand the sum of that. Now these are kind of mathematical definitions in foundation, but this is only going to be useful if you can find a formula or pattern for the nth partial sum. And that is usually exceptionally difficult. Now, before we get into some specific examples, like what you'd be working on in the homework, let's take a look at a few examples where we can actually find a formula for the sequence of partial sums for an infinite series. All right, let's start with a first one. This is the infinite series where the terms are 1 or -1 being added forever. This is what's known in mathematics as Grandi's series. And this was kind of used as the mathematical proof for the existence of God. Maybe as a follow-up video, I'll have you take a look at a quick mathematical proof that Grandi used as proving the existence of God, something coming from nothing. But we'll save that for maybe a follow-up video. All right, we're going to look at the partial sums here. So we just start with the first term, which is 1. S1 is then just 1. We now move on to our second partial sum, which is adding up the first two terms, 1 and -1. Those add up to 0. And you can probably see what's going to happen here as you add up an odd amount of terms. You're going to get the terms from this infinite series summing to 1. And if you add up an even amount of terms, you get 0. 1 and -1 would be in pairs for an even amount of terms. So we get this nice simple formula here for the nth partial sum. S sub n is either 1 or 0, depending on if the index n is even or odd. All right, we can take a look at now the limit of this partial sum. And notice the limit here for S sub n does not exist since S sub n is approaching two different values, 1 or 0. And since we have a quantity here approaching two different values, the limit does not exist. That's the limit for the sequence of partial sums. What that tells us, since the limit of partial sums does not exist, our infinite series here is divergent. Let's move on to a second example where we can find a formula for the sequence of partial sums. All right, our terms here are just 1, 2, 3, 4, 5. As we start to add up more terms, our first partial sum is just 1, adding up just the first number 1. Notice your second partial sum would be 1 plus 2, 3. Move on to your third partial sum, which is now adding up your first 3 terms, 1 plus 2 plus 3. This comes out to 6. Add up the first 4 terms. The fourth partial sum will come out to 10. Add up the first 5 terms, 1 plus 2 plus 3 plus 4 plus 5. You get 15. The sixth partial sum would then have 6 added to that, which would give 21, and then so on and so on. Now there's a nice little mathematical tangent here we can go off on that popped up back in kind of the end of the 1700s with a mathematician called Carl Friedrich Gauss. And the story goes, when Gauss was in elementary school, like kindergarten or first grade, he was brilliant and he was annoying his teacher. So the teacher basically said, all right, go off to the corner, add up the first 100 numbers. And the teacher thought this would take him like all day to do. Well, the story goes, Gauss came back basically a few seconds later with the correct sum, but he did it in a very tricky way. All right, this is going to relate to our problem here of finding a formula for the nth partial sum. So bear with me. Let's say we wanted to add up the first 100 numbers, 1, 2, 3, all the way up to 100. Now, what Gauss noticed is if he reversed the order and added them up from 100 going down to 1, so 100 plus 99 plus 98 down to 3 plus 2 plus 1, what he noticed is that if we group those terms in pairs, we always get the same sum for the pairs. Notice if we were to add up 101, you get 101. Add 99 and 2, you again get 101. 98 plus 3, again 101. And every pair here added in this reversed order gives 101. Now, if you count there how many 101s you have, there's 100 of them. So what Gauss noticed is if he adds this finite sum to itself in reversed order, he gets twice the sum he's looking for, but that twice the sum is the 101s being added together. Repeated addition, you can write as multiplication, and what he found is twice the sum was 100 times 101. If you solve that for the sum s, just divide by 2, you get the correct value for the sum of the first 100 numbers, 5,050. Now, Gauss was one of the greatest mathematical geniuses in all of history. So no surprise he was able to do this, but it's an interesting little trick that we're going to bring back to our infinite series here. All right, we can do that similarly for the first n numbers, and if you repeat that argument like we did, as Gauss did for summing up the first 100 numbers, you can get a formula here for the nth partial sum, the sum of the first n numbers, as this. S sub n comes out to be n times n plus 1 divided by 2. And notice there, if you plug in different values for your index, start with 1, 2, 3, 4, and so on, this formula for S sub n does give the stated, right above there, correct values for the nth partial sums for S1, S2, S3, and so on and so on. So we have found, kind of mimicking Gauss's idea, a formula for the nth partial sum here. This one, we're going to take a look at the limit for that sequence of partial sums. Notice since all the n's are in the numerator, as n goes to infinity, this nth partial sum is just going to keep growing and growing and growing as n approaches infinity. And what we find here is the sequence of partial sums in this example, that limit for the sequence of partial sums approaches infinity, which as a limit we say does not exist. What that means then is this infinite series, 1 plus 2 plus 3 plus 4 plus 5 forever, is divergent. Now this one we're going to have some interesting things to say. Think back to our intro. We said this has a peculiar sum also of -1/12. Notice with our basic understanding of convergence or divergence of an infinite series, about relating that to the sequence of partial sums, we see here that this infinite series is divergent, which basically means that the sum, adding up all those terms, comes out to infinity. And that is our most basic way to understand the sum for this infinite series, 1 plus 2 plus 3 plus 4 plus 5, forever. The negative 1/12 answer we said, that was also mathematically correct, that comes from a more advanced way to understand convergence or divergence, adding up an infinite amount of terms, something that we'll see later in the course as a kind of a nice little follow-up. All right, let's take a look at our final example of an infinite series where we can find a formula for the nth partial sum of that terms. And this one's going to be very important. We're going to devote the follow-up lecture, kind of a second part to this, mostly dealing with these things called geometric series, since they're kind of the most important example of infinite series within the calc sequence. Now they have a very simple nth term. A sub n is some number a times an nth power of another number r. And notice your terms here for the infinite series start with n equals 0. You would have r to the 0, which is 1. Our first term now would be just a. Each successive term just basically gets multiplied by an additional factor of r. So the first term of the infinite series is a. The second one would be a times r. The third would be a times r squared, then a times r cubed, so on and so on. Now what makes geometric series kind of important is all the terms, if we were to divide them by the previous term, all have the same value, r. And that's what we call the ratio. For a geometric series, the ratio of a term divided by its previous term is always the same number, r. Notice for the terms here in our infinite series, if we were to do that, take a term, for instance, ar, and then divide it by the previous term, a, that cancels to r. Take a look at the n equals 2 term, ar squared, divide that by the previous term, ar, that also simplifies to r. And that pattern continues if this is what we're defining as a geometric series. The formula here doesn't tell you what a geometric series is, but it's basically one where the terms are an nth power of some number. We refer to a here as the starting value. Notice the first term in your infinite series is a, and we refer to r as the ratio. Now, if we go back to Zeno's paradox, let's start with the n equals 0 formula. N equals 0 referring to the starting index. This is a geometric series where the first term, a, is 1, and the ratio r is a half. All right, let's take a look at a different geometric series. Let's say one where the starting value, a, is 2, and the ratio, r, is 1/3. And we have this formula here. And if we were to write out terms starting with n equals 0, we get for our first term 2, then 2/3, then 2/9, and then 2/7, just slowly incrementing the index n one value at a time, starting from 0. All right, now this is one where we're going to reference back to being able to find a formula for the nth partial sum. And there's going to be 4 possibilities, that all depending on the value of r, the ratio. All right, let's start first with the case r equals 1. Every term in your infinite series, since 1 to any power is 1, all the terms here are just a. And if you were to add up, even if a is a very small number, add a number to itself an infinite amount of times, that's going to keep growing and growing. The sequence of partial sums here has a simple formula, a times n, depending on how many a's you're adding up. And in this case, the limit for the sequence of partial sums would approach positive or negative infinity, depending on if a is positive or a is negative. So the r equals 1 case gives a divergent infinite series. All right, we can move on to now, let's say the possibility where r is -1. Similarly here, we get something to similar to what we saw with the infinite series -1 to the n. Add up the first odd terms, you get some cancellation, and you should have a minus a canceling out, leaving you over with a for the case of an odd partial sum. And if you were to add up an even amount of terms, a minus a in pairs, that's going to add up for the partial sum when n is even to 0. This approaches 2 different values. So again, this sequence of partial sums does not exist, giving us a divergent infinite series. All right, there's the possibility where r is bigger than 1. And notice here we have r in absolute value. So it could be a number that's positive or negative that's large. If the ratio is bigger than 1, all your terms here, a times r to the n, get bigger. And if you think adding up numbers that keep getting bigger, you shouldn't get a finite sum. It should become infinity. So we'll say quickly here, in this case where r is bigger than 1, we get a divergent infinite series. Now so far, that's 3 possibilities, all of which lead to divergent geometric series. Now there's a 4th and final possibility, which is of interest, where we don't get a divergent infinite series. And this is the case where r, the ratio, in absolute value is less than 1. These are now where the ratio are now small numbers. So our terms here, a plus ar squared plus ar cubed, so on and so on. Now our goal is with this infinite series is to add up the first few terms, giving us partial sums. All right, if we were to do that, we get this set of expressions here. First partial sum is just a, second partial sum a plus ar, and then so on and so on. All right, we can write down the terms for the nth partial sum. We start with a, but notice because things are a little bit shifted, we're starting our index with 0, the last power for r that we have there. It's not r to the n, but r to the n minus 1. Take a look at the previous partial sums. S2 ends with r as the highest power. S3 ends with r squared, and S4 ends with r cubed. So S sub n ends with n minus 1 as that final power of r. All right, now this one we actually can find a nice simple formula for S sub n, one that we can take a limit of. And again, this was kind of another trick. I'm not quite sure who this is attributed to, but we're going to take that expression for S sub n, and I'm going to multiply everything by r. So if I multiply all finite number of terms there by r, notice each expression, just each power of r goes up by 1. When you multiply, you can add exponents, provided the base is the same. All right, so we did that. We took our expression for S sub n, multiplied everything by r. Now what we might notice is there's a lot of overlap in terms that appear in both expressions. Notice if we group them kind of diagonally here, we have AR appearing in the above and below expression. We have AR squared, again, appearing in the above and below expression. And that pattern continues, leaving us here with the first term, A, and the last term, A times R to the N. Those aren't paired. Now, what we are going to essentially do from here to get a formula for S sub n is we're going to subtract these equations. Notice, since there's a lot of pairs, those pairs are going to subtract to 0. They're going to cancel. What you should be left with is A and R, or A times R to the N. Now, at this point, pause the video, see if you can finish solving this expression for S sub n, the nth partial sum. All right, welcome back. Notice, since we have S sub n on the left side, we can factor that out. I can factor A out from the right side. And if I divide by 1 minus R, we have now solved for S sub n, getting it by itself. And we get our formula here for the nth partial sum, A times 1 minus R to the N divided by 1 minus R. And recall, this was the possibility where the ratio in absolute value is less than 1. Now, what we want to do is take the limit of S sub n as n goes to infinity. Remember, for convergence or divergence of infinite series, we look at the limit of the sequence of partial sums. And that expression, R to the N, since R in absolute value is less than 1, numbers less than 1, when you do increasingly larger powers, they get smaller towards 0. So in this expression, the R to the N in the numerator, that approaches 0 as n goes to infinity, leaving us with this finite value for the limit, A divided by 1 minus R. Since we get a limit here that is a finite number, this limit for the sequence of partial sums is convergent. And what that tells us, since the sequence of partial sums has a limit or is convergent, the infinite series is also convergent. And what we get is our final conclusion here for all the possibilities for a geometric series. The geometric series will occur in 2 versions. Both formulas are a number A times R to either an nth power or R to the n minus 1th power there. Notice the starting indices are different, n equals 0 compared to n equals 1. There's 2 possibilities, all depending on the values of R. If R, the ratio in absolute value, is less than 1, we can say that equivalently if the values of R are between -1 and 1, then we have a convergent infinite series, and the sum, we define it as that limit value, A divided by 1 minus R. If the ratio in absolute value is greater than or equal to 1, the geometric series is then divergent. Now we're going to take a look at some examples right after this. Those are all included in the second part of this online lecture.